start streaming to YouTube. Let's do this. Okay, so we're going to pick up where we left off last Thursday, which was about numerical distributions. So let's go to writing mode. Okay, that doesn't look right. This is not the right writing mode. Okay, close little peep. Okay, wrong writing mode. Okay, it's... There we go. Cool. So let's just quickly talk about what we did last week. So, we started talking about distributions of variables. So you have to remember that a distribution of a variable means that you look at everything at once. It's sort of like the whole idea. Okay, and you're looking for trends or patterns. Now, how you're going to do this is going to depend upon the type of variable that you're dealing with. Okay, so you either have a numerical variable or a categorical variable. We've been talking about how you look at the distribution of a numerical variable. So we did this example where we talked about a number of siblings, right? And if you ask people how many siblings do you have, their responses will be a numerical variable because it counts, right? It's a discrete numerical variable. And we talked about different ways to visualize this. One of the ways I showed you was the dot plot. Okay. And then we started talking about the center of the distribution. Okay, so we talked about the mean. And hopefully you guys all remember that how do you calculate the mean? You add up all the different numbers and divide by the number of numbers. So you could see like here's like the calculation where that happened. And we found out for the people in this class, the typical number of siblings or the center of the distribution was 2.55. And we talked about how this is like sort of weird because you can't have 2.55 siblings. So what would it mean for it? What does it mean to say typically people have 2.55 siblings? Forget about that for now. We'll get back to that in the future. There's some issues with using the mean for this, but it gives you an idea. And we also discussed why the mean was important. So does anyone remember, if you have the dot plot, what did the mean tell you? Let's see if people remember. So like, the 2.55, like what was special about that number on the graph of the dot plot? Let's activate everyone's knowledge from last time. I know it's been forever. Yeah, exactly. The mean, what's really cool about it is that if you think of all those dots as like weights on a seesaw, the mean is exactly where you would put the fulcrum, the point where it tips, so that it would balance. Which is actually why it's one of the reasons it's really useful. Okay, good. People do remember. My job has been done so far. Okay, so we talked about that, and then we finished with talking about a histogram, which was another way of displaying the information. Okay, now with the dot plot, you have a dot for each number. What was different for the histogram? Let's see what people can recall. Like, what was different about it? Yeah, so what you do is you shovel them all into a bin. So the example I gave was one of our bins will count all the numbers from 0 to 3. Another bin will count all the numbers from 3 to 6. Okay, so how many numbers were between 0 and 3? Apparently 7. How many numbers were between 3 and 6? Also 7, because the bins were the same height. There was something weird about the way the bins worked. So if I say that includes the numbers from 0 to 3, that's not quite true. What's the caveat to that? I'll dance while I wait for people. Swinging to Little Peep in the background. But there was an issue with this. We sort of talked about it. The bin, if I say from 0 to 3, that's not quite true. Do we remember? Yeah. So if I'm talking about like a bid from 0 to 5, and then a bid from 5 to 10, like that's not quite like, do you see how 5 shows up in both of them? Like there's an issue with this. I talked about it last time, but I'm trying to activate that. Yes, so the left-handed number is included, but the right-handed number is not included when I give you. Yeah, yes. Yeah. That's how it's always going to work for us when it comes to the bins. Oh, this is weird. Okay. Okay, cool. So now we're going to talk about looking at these histograms, what the histograms can tell you about the distribution. So now would be a good time to tell you, what are all the things that we care about when it comes to distributions? Okay, so when we are discussing distributions, or numerical distributions. When we are discussing the distribution of a numerical variable, we care about 4 properties of the distribution. And we actually care about these properties in a particular order. First, we care about the shape of the distribution, and I'll explain to you in a moment here how you figure out what the shape is. We care about whether the distribution has outliers. I'll explain to you what that means. We care about the center of the distribution, in other words, the typical value. We already discussed this. Remember how we were talking about the mean was a measure of center? We'll talk about other numbers or other measures of center. And then we care about the spread of the distribution. That we'll discuss that later. Okay. And they're in order because to do this properly, you first need to know the shape. And then you need to look at whether there's outliers, and then you can talk about the center, and then you can talk about the spread. The acronym that people usually use to remember this is SOCS. S-O-C-S for shape, outlier, center, spread. Okay, and something's weird with my tablet. One second, I need to like troubleshoot like what the hell is happening. It's like making it like write it all weird. Oh, okay. I only want it to work on monitor 2. That's the problem. Okay, awesome. Okay. Oh, there, thank God. Okay, cool. Fixed it. Okay. So we're going to talk about all the different parts of this. So let me open up a Wolfram. I hear like cartoons in the background. Is like someone watching cartoons? Or TV or something. Sounds like Spanish language TV. Okay, so let me change my window capture. Okay, I don't see it. Where is it? Okay, sorry, one second. This is like driving me crazy. It's like not letting me switch the window. There we go. Yes, there we go. Okay, so let's go to Wolfram. Oops. Let me sign in. I'm gonna make a new notebook. There we go. Okay. So, let me load in some data. So I'm gonna go to the Open Intro website, and I'm gonna the data we're gonna look at is gonna be. Oh, let's do the age at marriage again, since we talked about that last time. Okay, so I'm going to go to the CSV file. I'm going to copy the link. Okay, so I'm going to say data equals, and I'm going to import, paste in the link. Let's put some space so you can see it. Okay, then I have to put comma, header lines 1. Okay, then we also have to put data set. Okay, and I'm gonna mute someone because I don't want to hear your stuff, no offense. So I'm just looking through, trying to figure out who has their mic on. It's you, Karen. There we go. There, that sounds so much better. I was like having a hard time thinking. Okay, so back to this. There we go. Okay, so let's load the data. Boom. Okay, it's loading. Okay, we've got our age. Okay, so remember, if you want to make the histogram, you have to start with the data. You tell the computer you want all the rows, and then you tell it the variable you want. We want the age variable. And what is the next thing you have to do if you want to make the histogram? Awesome, yes. So / histogram. Boom. And you get the histogram. Okay, now what's really nice about working on a computer is that if you want to, like, Wolfram can make this picture for you, and then what you could do is just copy the image and like put it in a Google Doc. Like, does that make sense? Like, or you could just use the Wolfram, you know, you can use the notebook and put stuff in there. So what I'm gonna do is I'm gonna copy this image. I'm gonna paste it into OneNote, so that we can like draw it. Oh wow, okay, that did not work right. Oh, whoa, okay, it like did not let me copy it, what the hell? Copy as image, there we go. There we go. Okay, so apparently if you want to copy the image, you have to click on the little, does everyone see the little, what's the word? Gear on the right-hand side? There's a little gear. It's like, I'm making it blink right now. Okay, you have to click on that, and then you'll see copy as, and you have to choose image. And then you say, right-click on that, and then say copy image. Okay, so I'm going to paste that into OneNote. There we go, cool. Okay, now we're going to go back. We'll return to Wolfram in a minute, but we're going to look at this in OneNote. Okay, so let me change our setup. Let's go back to OneNote. And it disappeared on me. There we go. Cool. Okay, does everyone see, do we see the histogram in OneNote? I just want to know. Is it showing up? Okay, cool. Okay, so here it is. So I'm going to talk to you about how you look at the histogram to figure out what you need, the shape from it, basically. Oops. Sorry, I'm like readjusting my screen. Okay. Okay, so when you're looking at the histogram, you need to look for what's called the mode. The mode is the bin with the highest count. In other words, the tallest bin. Okay, because the way the bins work is that the more subjects that are in that bin, the taller that bin gets. So if you look at this, the tallest bin is this one right here. And if you go, you can see that it is approximately a little less than 500 tall. That means there are almost 500 women who first got married. This bin looks like it's about 21. Okay, so in our data set, it looks like the most commonly occurring value was 21. So in other words, what was the most common value? Was about 21. In other words, what was the most common age at which women first got married? 21 years old. I.e., typically, women marry for the first time at about 21. Okay. Okay, so does it make sense you look for the tallest bin? Good so far? Okay, I'm going to put a line through it. Okay, we're going to call this our center. Or you could call it the mode, whatever. So for a moment, you're like, the mode is going to be what I think of as the center of the graph. Notice I put center in quotes, because do you see how it's literally not in the middle? We're just calling it our center. Now, what you do is you use the center to measure the length of what are called the tails. So there's a right tail and a left tail. The right tail starts at the center and goes out all the way to the very last bin. So you see how the last bin is like right here? So you see how I made that little line, the red line that goes all the way out to there? Okay, so this is the right tail. Okay, the left tail works also pretty similarly. You start at the center and you measure to the first bin. So like right to about here. That's the left tail. So what do you notice about the tails? I also know that people are writing, so don't feel super pressured, because I know it takes a moment to sort of draw the histogram. Yeah, the right tail is longer. So whenever one tail is longer than the other, we call that a skewed distribution. So let me write that down. Oh, don't worry, I'll say it again. Let me just type it as I say it. So, if one of the tails is longer, and we'll talk about how much longer it needs to be later. And let's say noticeably longer. Noticeably longer than the other. We say that the distribution is skewed. Okay, then you have to say in which direction it is skewed. So do you see how the right tail is longer here? We would say that this is right skewed. Does it make sense? It's right skewed because the right tail is longer. You can also be left skewed, right? Depending upon which one is further. Oh, I should not have put the skewed there because it got cut off. Let's put it right here. So this is right skewed. Oops, can't write. So this is right skewed. Why? Because the right tail is longer. If the left tail was longer, it would be left skewed. Mm-hmm. Yeah, if they're like fairly close, but one side is actually literally longer, if you like broke out a ruler and you're like, oh, this one's 2 inches long and this one's 1.8 inches long, like obviously one is longer, but you'd see that they look pretty similar. You wouldn't say it was skewed. And I'm going to talk more in the next thing about how you can like more easily tell. Well, that's a good question though. But because it does need to be quite a bit longer. They can't just be like pretty close, but oh, one is technically longer than the other. We allow ourselves some wiggle room. Okay. Okay, so I'm going to leave this up, but we're going to go to Wolfram and we're going to get some other data to make another histogram, and we're going to hopefully find something that's left skewed and there's another shape that the distribution can have. So I'm getting the link to the ACS12 dataset, and we're going to load that one too. Okay, so let me change my screen. Okay, so I copied the link to the ACS12 data, the American Community Survey data. And I'm going to call this data ACS12 equals import. Whoa, going really slow. Okay, import, paste, name of the data, comma, data set, header lines. Oh wow, like my computer is like really lagging. Header lines 1. Okay, let's load the data. Okay, there's my data. Okay, we're going to look at the variable. Which one should we do? Should we do how many hours they work, or should we do their age? Hours worked or age? Cool. Okay. So we'll say, let's take our ACS12 data. So I write ACS12. Oh my god, it is going so slow. I already typed it in and it's like, you know, like when there's extreme lag. Oh my god. Okay, so all the rows, and I want the age, / histogram. Oh, well, it was so slow I wrote histotogram. Okay, that should be histogram. Oh my god, I don't know what's wrong with my computer, but it's like almost unusable. Like, I'm like pressing erase and like nothing happens. Okay, there we go, rerun. Why do you hate me, computer? There's my histogram. Okay, so I'm going to copy this as an image. We're going to put it back in the notebook and we're going to look at this. Okay, so 1 second. I'm just going over. Sorry, my computer's just like crazy lagging right now. Okay, what is going on? There we go. Wow, my computer is just like struggling today. This is just the struggle bus. Okay, there we go. We're back. Okay, so hopefully, do you see the histogram? Is that what's like showing up now? Okay, cool. Okay, so this histogram's a little interesting. So you have the age. What's the youngest people? Remember, this is the age variable. So what are the youngest people in my data set, approximately? Yeah, so the first bin, it starts at 0 and it looks like it goes from 0 to 5. So you have people all the way from newborns, all the way up to what? Like, approximately how old does it seem to go to? Well, yeah, let's look. So if you can see how from 0 to 20, there's 1, 2, 3, 4 histograms. So that's 20 wide divided by 4. So how wide is each bin? 5. So 80 to 85. 85 to 90, 90 to 95. So pretty close. But the whole point is I'm trying to show you can actually figure it out. So you see like there's two numbers, 0 to 20. You know that that's 20 wide, and you can see that there's 4 bins that cover it, so you can figure out how wide each bin is. So I would write that down, that you can find something of a certain width divided by the number of bins you see there, and you'll know how wide each bin is. So let's write that down so you could... Okay, it's not letting me type. Please, computer, let me type. No! Okay, I'm just gonna write it. Okay, so find 2 numbers and then divide by the number of bins between them. Divide by the number of bins. Okay. Now, remember last time I talked about finding the mode? Okay, there's something sort of interesting about this graph. Does everyone agree that this is the highest bin? So that would be the mode. Okay, but what you notice is, do you see how like this one over here and this one over here are also pretty close to the mode? And in general, if you look at all these, they're also fairly close. Okay, so let's compare that to the previous histogram. So do you see with the previous histogram, there was an obvious high point, and then do you see how it like fell? Like the heights of the other ones like consistently went down smaller and smaller and smaller afterwards? Or do you see what I mean by that? There's the high point and then all the other ones fall down. Okay, if you look at the new one we have, that trend doesn't really match here. If you have a mode, it should fall like this afterwards. Like, do you see how on this side it definitely gets shorter, but on the left side, do you see how like the height basically stays the same? So if you see something like this, where there's a whole section of the graph where the bins are about the same height, we call that uniform. Uniform is when there is no real mode. They're all about the same height. Okay, so we would say that this is a uniform distribution. almost. It's not quite, but it's pretty close. So we're talking about the shape here. The previous one was a right-skewed distribution. This is pretty close to being a uniform distribution. And actually, there's a pretty good reason for why this is the case. Up until about here at the green line, do you see how the heights are the same up until there? And then the heights start falling afterwards? Why does that happen? This is actually a really good question. Why did the heights of the bins fall after where I drew the green line? Approximately where is the green line? Cool. What starts happening to people once you get past 70 years old? Yeah, so does that make sense? There's fewer and fewer and fewer and fewer people past the age of 70. Now, that means if to the left of 70 is the people younger than 70. In other words, there's about as many people who are 0 to 5 as there are 5 to 10, as there are from 10 to 15, as there are from 15 to 20, right? Those are about all the same, right? Because it's not like something's killing them off. Okay, so it's pretty, the number of people under the age of 70 in each of the age categories is fairly uniform, and then it starts dropping. So it makes sense, that's why you'd see this data. And this sorts of stuff happens a lot in the real world, which is why we distinguish between them. Okay, so if you see like, oh, all the bins are about the same height, we would want to say that that's uniform. Good so far? Okay, we're gonna do another one. But I'm gonna leave this up here for a moment. I'm gonna get another histogram ready for us while you guys are typing. Because it's gonna take me forever to type it in. Oh, yes. Thank you for turning on your cameras, people. I showed you guys that meme of the two Doges, right? Yes, yes. I'm no longer alone. It's sort of weird. It's sort of voyeuristic when you think about it. Like, everyone sees me, but, like, I don't get to see you. I think that's, like, rather unfair. Or, like, I don't get to see most of you. I know, I always wonder that too, like with the Doge meme where it's like, please someone respond. Can someone please? Okay, so I'm gonna put in a new histogram. Okay, and I have to change the size. Oh, whoa, what the hell happened? There we go, that looks good. Okay, this is the histogram of the variable hours worked. There is a very obvious zoom is. Oh, yes. Someone messaged me, Zoom is trying to come out with something where students can choose only to have the professor see it. A lot of female students have told me that they're creeped out by like people's screen cap and stuff. So that is actually pretty understandable, which is why I don't like require that. Yeah. So, oh my God. Okay. Disclosure. I have a friend who's studying for the medical license exam. So that's like the examinations when you are finishing med school to like get certified to become like a doctor, right? Does everyone know what I'm talking about? There's like tests they have to pass. And she signed up for, so like doctors, they'll teach these classes, right? Because they've passed it. So they'll like make side money that way. And the guy, he teaches the class on Zoom, right? And my friend is a fairly attractive woman, let's just say that. And the guy was like always messaging her like, you have to turn on your camera. And she was like telling me like, is that like something you do with your students? And I was like, no, I just say if they want to turn it on, they can turn it on, you know, or like, it's completely up to them. I would never be like, hey, yo, whoever you are, like turn on your camera. And the guy like disabled the chats between people, and like apparently a couple other female students like messaged her, and they're like, does he ever like say that you have to turn on your camera? And they like talked about it, and she was, and this was after I told her, I was like, that sounds really suspect. Like, I think he's just a weirdo. And then like afterwards they found each other on Facebook. And then, like, they all connected and said, like, yeah, he does that to me, too. So, yeah, exactly. So, creepy as hell, yes. There are weirdos in the world. Surprise, surprise. I mean, it really sucks, but I don't think anyone's surprised. So, anyways, back to statistics. So, hours worked here. We have an obvious mode. Why is this not surprising where the mode is? Yeah, it is very nasty. There's also creepy students out there. Yeah, that's why I was saying that, like, that's why I'm never gonna, like, force you to turn it on. But why are we not surprised by the mode? Well, yeah, so there's, like, a bunch of people who work full-time, right? So we're not surprised that the bin that goes from 40 to 45 seems to be the mode because of all those people working full-time, right? So it's sort of interesting. This is why distributions are cool, because you look at them and like sometimes you're like, oh shit, there are like way more people who work 40 hours a week than other numbers, and you're like, why? And then you think about it for a second and you're like, oh yeah, that's right, that's like full-time work, so there's going to be a bunch of people who do that. So let's draw the little line there. Okay. And let's measure the right tail. So the furthest out a bin seems to go is to about 100, right? So in other words, this right tail is about 60 wide. Does it make sense it's 60 wide because it goes from 40 to 100? Okay. Likewise, the left tail goes from 40 to 0, which makes it 40 wide. They're pretty close to being symmetric, or the same, but they're not. You can see that it definitely goes out further to the right, but I want to point something out to you here. So we talk about the shape, and then there's something about whether you see outliers in the graph. We're going to talk about that right now. So you have this bin right here, the 95 to 100. Do you see how there could have been bins here, but it's empty? Does everyone see how like there are no bins there? There is a bin right here, but then there's like empty spots. An outlier is where there's some sort of gap of empty stuff. There could have been bins, but there weren't. And then you get this little island of people. So this over here is an outlier. So an outlier means that it's separated from the rest. There's a bunch of empty space. And there should be very few. The height of the bin should be very small. So does everyone see how, like, in comparison to the mode, that little bin there on the edge looks really small? So if you see a gap and then a very small bin at the end, you would say that that's probably an outlier. Okay. Outliers are very untypical values. So the mode is like what's typical. It's typical that people work 40 hours. And then there's this other one, this other bin right here. It's untypical to work 100 hours a week, right? If someone told you they were working 100 hours a week, you'd probably be like, holy shit, like, why are you doing that, right? Like, that's crazy. Like, no one else does this. That's what it means to be an outlier. Okay, so you can identify them on the graph by there should be some sort of blank space and then a very small bin at the end. Now, notice the side with the outlier is which tail? The tail which is what? And the right tail is what compared to the left tail? Yes, the side with the outliers is the longer side, typically. So they go together. You've identified that there are outliers on the right side, which means that we would say that this is right skewed. Oh, shit. Crap. There we go. I closed it on accident. Okay, it's back up. Okay, because someone was asking earlier, like, well, what if they're about the same length? Well, one of the ways... So do you see how you're looking at this? You could look at this and you could say, I don't know, the left tail looks pretty close to the length of the left tail. The left and the right look about the same. Does everyone sort of agree if you're just eyeballing it, you might look at it and you're like, it's pretty close to being the same length? The thing that would push you over the edge here is, oh, there's an outlier on the right-hand side. That one... That's would be evident. And then you would measure it and you'd be like, oh yeah, the right one is actually longer than the other. And due to the existence of an outlier, I would say that it's right skewed. Okay. So I'll give you a moment to write that down. I'm going to get another histogram going. So just give me a second. Thing is really struggling. Just give me a second. I think my computer's just given up on me. Something's wrong. Maybe this will work better. Okay, there we go. Okay, let's copy the image. Copy graphic. Okay, let's paste. Okay, that is way too big. Still way too big. Okay, I'm not going to tell you what this variable is for. We're just going to deal with it. Okay, so let's look at this. When you're looking at the histogram, what is the first stuff? What's the first thing you ask yourself? So here's a histogram of some variable. Let's not worry about what the variable is. So what's the first thing you identify? The mode. Okay, cool. You look at this and you're like, okay, the mode's right here approximately. So let's draw the line. It's around like 0, right? Pretty close to 0. Okay. And now we measure out the right tail. It goes out to about what number approximately? Yep. You can figure that out because you can go from 0 to 1, and there's 2 bins that go from 0 to 1, right? So it's half a wide. So you see there's a number 2, so this must be 2.5. You go the other direction. There's your left tail. And it goes out to about -3. Right? So the right tail is about 2.5 wide. The left tail is 3 wide. And you look at those numbers and you're like, those are pretty close to each other, right? Remember how I said like, oh, they might not be exactly the same. So these two numbers are like, I don't know, 2.5 and 3 are pretty close. So if they're pretty close, what do you look for next to decide if the one is longer than the other? The existence of what? That we were just talking about. Yes, do we see an outlier here? Is this last bin an outlier? For it to be an outlier, what would you have to see? Yeah. Is there a gap there? No. So this is not an outlier. So because that's not an outlier and 3 and 2.5 are pretty close to each other, I would say that the tails are the same length. They aren't literally the same length, but does it make sense that they're close enough to each other? And since one is not an outlier, I can't say that like one is noticeably longer than the other or appreciably longer than the other. So as far as I'm concerned, they're the same length. Yeah, there'd need to be. This would have to be like out here, over here somewhere, and like blank. Mm-hmm. Okay, now because the tails are the same length, it is not skewed. This is what we call symmetric. The shape is symmetric. So we would call this a symmetric distribution. So there's basically, when you're talking about shape, there's like 3 possibilities. It could be symmetric, it could be skewed, could be uniform. Notice this all works the same. You start by identifying the mode. When it's uniform, you'll be like, there is no mode. They're all about the same, right? And if you have a mode, then you start looking at the tails and look for the presence of outliers. So that's why that's in that order. Remember how I said shape and then outliers? And then there'll be the center and the spread. So I would say, in terms of shape, this is a symmetric graph. In terms of outliers, there are none. And this will be a pretty good place to stop for today. Next class, we're going to talk about what's the deal with the center and what's the deal with the spread, the next two parts of that acronym. So I'm going to stop the recording. I'll leave this up. But like, there's only like 5 minutes left, right? So like, there's no point in like